An entire chapter was spent on solving systems of equations. In other words, equations in the same variable, that we would try to find the x and the y that worked for both. This same idea is generally true of inequalities, but the tricky thing is that inequalities can have so many solutions. So how can we show them? Last night we were focusing on how to graph linear inequalities, and so we would graph the line and then shade above and below because the y could be either something. The y coordinate, which tells us how high or low, would either be above, below, or on the line. So I've already taken this system of equations, this one, so two equations, or inequalities, excuse me, in the same variables. In other words, the same x's and y's. And we need to figure out how to find out what solutions would work for each of the systems of linear inequalities, each of the linear inequalities. The problem is that since we know from shading below or above that there's a whole region that could work. So really, to solve these is simply based on that same idea. As you can see, I've already solved each of these for y, because that was our first step, was to solve each inequality. Last night we only had one, but solve each inequality for y, because after that you can graph the related equation and then shade accordingly, according to the inequality sign. I'm not going to rehash that because I think you know. So I've made the first equation in red. I think you all know how to solve for y, so I'm not going to go through that. To graph the related equation would be to graph y equals x plus 3. So I know that I begin up at 3, and from there I'm going to go up 1 over 1, up 1 over 1. And since this equation says is less than or equal to, I know I need a solid line. I'm going to put my arrows. And we know that it's all of the y's below or on that line. So this region gets shaded in red below the line because we're looking for the y's that are less than, and that means below. The other equation, when I solve for y, I get y is greater than negative 2/3 x minus 2. So this one begins at negative 2. From there, I go down 2 and to the right 3, or that also means up 2 and to the left. So we can see that this is the line, and it is, in fact, a dotted line. So I'm just going to put in a few more dots in between. And this one is all of the points greater than. So I can see that it's all of the points above. Now, since I've already shaded the red line, we're looking for the part that overlaps. So you can pretty well see this, that this is the space that overlaps. And in fact, if I pick any of the points in this region and plug them in, plug the coordinates into each of these equations, I will get the actual answer. I'm going to just make this clear. I'm going to erase the part that doesn't get included because we're looking for the overlapping region. So there's that. We have our the dotted line of the blue. So the place that's shaded in both blue and red represents the solution to the system. So if I pick this point right here, that is the point 1, 2, 3, 4, 2. and I plug in 4 for x and 2 for y, I say 2 minus 4 minus 3 is less than or equal to 0. It's certainly true, because that's negative 2. Negative 5 is less than or equal to 0. And if I plug in for x, 4, 2 times 4, and for y, 2, that will be greater than negative 6. 8 plus 6 is certainly greater than negative 6. So this is one of many solutions, anything in this region. So the overlap equals the solution. Any of the points, the x and the y's, in the overlap make the inequalities both true.